Okay, we are in section 15.2. In 15.1, we already showed that the Legendre polynomial p sub n satisfies the Legendre equation written in this form with the eigenvalue p sub n of the nth order set with the eigenvalue n times n plus 1. In this section, we'll talk about the orthogonality of these Legendre polynomial. Actually, we have seen in the general self-adjoint ODE the eigenfunctions are orthogonal, but for this particular case, we can derive the fact that they are orthogonal again. The derivation is quite straightforward. So, and we start with the Legendre equation. So, what we will do is multiply the equation by another Legendre polynomial with p m x. Multiply this, the whole thing. Okay, and now m is not equals to n for this case first, and both m and m's can be 0, 1, 2, 3 order positive integer and 0, but consider the case first, m is not equals to n, and then we integrate x from the whole range minus 1 to 1. Okay, we'll do that. And then we'll write this equation after the integration again, but with m and n interchanged. So we can write down another equation. So integrate dx, but now you multiply bn of x of a Legendre equation with for p sub m is there, and the Legendre equation for p sub m, of course, the eigenvalue is m times m plus 1. Okay, and then we subtract the two. So subtract one by the other. So subtract it. Okay, and what we will get is, so first is this minus that. Okay, so we'll write it like integrate x from minus 1 to 1, and then you have pm times d dx of 1 minus x squared dp sub n dx, and then minus pn d dx 1 minus x squared dpm dx. Okay, so that's this minus that, and then you have this minus that. We can move these two terms to the other side, to the right hand side, and move this. This is subtract, so move to the other side, becomes m times m plus 1. So both terms involve pn times pm, pn times pm, and integrate from the x from minus 1 to 1. So you get this minus that one. Integrate dx pn pm. Okay, so and then we can simplify this one. Okay, so and to simplify that, we can do integration by part for both of these terms, so this term and that term, both we can do integration by parts. So this is equals to Pm one minus x squared dPn dx and minus Pn 1 minus x squared dPm dx, and evaluate from -1 to 1 and subtract. When you do integration by parts, now you have this times the derivative of that, so it's 1 minus x squared dPn dx and dPm dx. Okay, and for this one, you subtract the same factor dPm dx dPn dx. Okay. Now you see that this the integral is exactly the same, because this is dPn dx times dPn dx, this is dPm dx times dPn dx, and multiplied by the same factor. So exactly the same. So the integral is 0. Now for the boundary terms, evaluate that x equals to 1 and minus 1. So both will be 0 because of this 1 minus x squared factor. Of course, assuming this p and dp dx is not singular. So the whole boundary term is 0. So this is 0. Okay, it means that the right-hand side is equals to 0. So this implies this integral will be 0 if m is not equals to n, because both m and n are positive number. So, except of course there's a situation where both m and n is 0, but then we already said that m cannot be equals to n, so one of them has to be non-zero. So this factor is non-zero. This implied the integration the two Legendre polynomial multiply together, integrate from -1 to 1 is equals to 0 for m not equals to n. Okay, so that's the idea. And the next equation in the textbook is just to show that if you change x from back to cosine theta, which is at first what we got the Legendre equation in spherical coordinate, and that can change. You can change this integration to an integration in theta. So, and the ex dx will be cosine theta. So theta will be from pi 0 to pi, means 0 is 1, pi is cosine pi is not -1. So d theta from 0 to pi, and dx is d cosine theta, so it becomes negative sine theta d theta, but you can flip the integration sign, becomes sine theta d theta multiplied by pm cosine theta pn cosine theta. That would be 0 again for m not equals to n.